So it's recording. Check the actual level of recording. It's all good.
So did you find out what was causing it to crash?
I have not yet, but I found out what works. So looking at the difference between what works and what does not work, I think it has to do with the USB 3.0 device that I have. Because in the other class I was using this, which is a USB 3.0 SSD, and the only difference now is I'm using thumb drives that are only USB 2.0, so they're slower devices. So I think it's not entirely backward compatible because the computer is older. This one is only USB 2.0 capable, but when you plug in a USB 3.0 device, maybe that's causing some of the issues. Because I don't have enough time to play with this computer. There's a class ahead of us. All right, so let's go ahead and get started. It's 9 o'clock exactly. So I'm hoping some of you have time to take a look at the last part of this slide here, which is all the way down here, the two examples. So did anyone get a chance to take a look at the examples? Okay, all right. So that's kind of important because now that we have talked about resolution, it's time to actually make use of all the things that we talked about earlier. Okay, so at this point, what I'm going to do is I will, just go over the examples, and if you want to ask me questions about this, we can go back to the earlier part and explain the mechanisms and stuff like that. So we'll look at the example, which is up here. Okay, so this is the example. The example is saying that this is really just for silly, just kind of make it a little bit more fun. Okay, but basically we have three variables. P, Q, and R are all variables, which means P by itself can be true, can be false. Q can be true, can be false. R can be true, can be false as well. And because they are variables, we don't exactly know whether they're true or not. On the other hand, we have some established truths or facts in the system. In other words, these WFFs are in iota, which means I don't know whether P is true or not. I don't know whether R is true or not. But I know for sure that P implies R is true. Is that okay with you guys? Okay. I don't know whether P is true or not. I don't know whether Q is true or not, but I know P or Q is true. Now, because we know what OR is, so we know that at least one of P or Q has to be true in order for the disjunction to be true. Okay? And then the last one is we also know that Q and R cannot both be true at the same time because the conjunction of QR is negated, and the negation is always true, which means QR, one of them cannot be true. At least one of them cannot be true. Okay. So are we okay with these three given facts? The things that is given to us in iota. So we don't really ask the question, why is that the case? Can we prove that? We don't ask those questions because they are given to us as facts. Is that okay? All right. So the first one has a theorem to prove, and it is R implies Q. In other words, given that these three are given to us, can we conclude that it is always the case that R implies Q? Now, from just from looking at the given to be true well-formed formulae, it may or may not be obvious whether this is true or not. But that's the objective of today's lecture, is how do we prove whether R implies Q is a theorem or whether it is not a theorem. If it is a theorem, it means that these three things implies this one thing here. If it is not a theorem, then the implication does not work. Okay? So do we have any questions about what we are trying to accomplish, at least in today's lecture? No questions? Yep, go ahead.
So the established facts in the system, that's iota. Is there anything else in the...
in the iota?
No, do these things up here, are they categories of anything else in propositional calculus?
Yes. So in terms of propositional calculus, they also have the same thing in propositional calculus. In other words, we are dealing with propositional calculus here. It's just that the mechanism to prove a theorem is not using the conventional one. We're using resolution to get it done. Okay? So we're still trying to prove a theorem. We're still using propositional calculus, but we're trying to use a very mechanical way to do it instead of going using the usual human way of doing it. Okay. So are there any other questions? Yep. Go ahead.
P, Q, and R and A.
Mm-hmm. P, Q, R.
Is what we want to prove zeta, or is how we prove it zeta?
We are not proving zeta. We are proving this particular thing, and we want to see whether it is a theorem or not.
Okay.
In other words, we are given that these things are true. Does it follow that this has to be true as well? That's the question. Is that okay?
Yeah.
So given that the sky is magenta implies everyone passes cisp440 and a whole bunch of other silly facts, can we also claim that R implies Q, or can we imply that everyone passes cisp440 implies all soy milk spoils? That's what we're doing, okay? But in the end, the meaning of P, Q, and R is really just for entertainment purposes. What really matters are these equations, or I should say, well-formed formulae. Okay, are we doing okay so far? Okay, so if you are not using resolution, then you will have to remember all those 20, 30 individual axioms and say, okay, which axiom should I apply here? And there's no end. You cannot really get to the end really predictably. Because when you think about it this way, okay, I can draw a picture. You don't have to. I'm not going to capture it on the projector. So the given facts are basically known points they can start with, and then each transformation rule or each axiom that we are using traditionally is basically just saying, okay, if you have these two things, we can come up with this, okay. And when you have this thing, you can come up with this thing here. When you have this thing, you can also come up with these two different things, and so on. So the inference rules are basically just mechanical transformations that basically say, if you start with this pattern, and this pattern here, we can end up with this one. If you have this one, we can end up with these two. But then we have some really odd ones. Remember this one? Starting with nothing, knowing nothing, I can tell you that the variable or the negation of the variable is true. Okay, so these things just pop up out of nowhere. Okay, in other words, you're coming up with these things. Okay, you start off with these three, and then you have a theorem to prove, which is all the way over here. This is your theorem to prove it. And the question is, how do you navigate through all of these things to this spot here? That's the question. That is basically what a proof is. A proof is really just saying, okay, I'm starting here with the known facts. I know where I'm supposed to be, where I need to go, and then I know how to go step by step to different spots. But you can go in a completely opposite direction and not know about it, using the more conventional way to prove things. And that's actually the difficulty of proving theorems. Okay? You don't have to answer this question, but for those of you who do not mind answering, if you do not like, or if you think that you're not good at proving theorems, what makes theorem proving difficult?
Just knowing all the basic rules.
Okay, so, but what if it's open book open notes? I can give you a list of the 30 rules that you can apply.
Sure, but there's still a lot on your paper, right?
There's still a lot on the paper, but the biggest question is, when do you use which rule in a productive way? Because you can be using the rules just fine. Okay, you can be using the rules correctly, but you're going in the other direction. You're going in the direction where it doesn't help. Okay, and that's because it only comes with experience. Okay, if you want to prove theorems effectively, it only comes with experience, and even with that, it's something that I cannot explain. Okay, the actual process of knowing when to apply which rule or which axiom when you're proving a theorem, I cannot explain that because it's all happening upstairs, and I cannot explain that process. Okay, it just pops up to me. Okay, So that's also why we are using resolution. So we'll see how resolution applies in this case. So when you use resolution, the first thing you need to do is to convert everything that you already know that is true, all the known to be true facts, into CNFs, okay, conjunctive normal forms. So we want to convert this into a CNF. We want to convert this into a CNF. We want to convert that into a CNF. Because once you have a whole bunch of CNFs, the conjunction of all the CNFs is also a CNF. Okay? So we want to convert in each individual piece into a CNF first. So I'm going to use a notepad here, which is also going to be helpful because you are going to do the same thing with your next homework assignment. So we have P implies R. We want to convert it into a CNF. So we say, okay, let's go ahead and try to convert this into a CNF. The first thing we do is we apply the definition of implication. So this becomes not P or R. Okay, so I'm starting to use a shorthand that is fairly common in computer engineering. In computer engineering, they look at OR as a plus, they look at AND as a multiplication. And the reason why that works is because in Boolean algebra, the place of the OR is actually what we would normally see as a plus, and the place where we use a conjunction is also where we would normally use a multiplication in normal algebra. So it just kind of works out really nicely. And then the exclamation point is borrowed from C++ or C, because it's just logical not. So this makes it makes it a lot easier for you guys to type, because you don't have to say \wedge and \v, / nig, for all of that stuff. This is a whole lot easier to type. Is that okay? Yep.
Why do we use 3 equal signs?
I'm just saying that it is equivalent to.
Okay.
So 2 equal sign would normally be enough, but I use 3 just to say that, okay, we are basically saying this is equivalent to that. Okay. So now we can say, okay, do we have it in CNF already? No. Yeah? It is in CNF already. Because it's a disjunction with only variables and negations of variables and nothing else. So by itself, it is already in CNF. This is one of the more kind of counterintuitive CNF because it looks like there's no conjunction in it, but if you really insist on the conjunction, you can do that. How about that? Remember, times or multiplication is conjunction, so I can always use and 1 to turn it into a real CNF. But that's just kind of extra and not necessary. So I'm just going to leave it the way it is. It is in CNF already. Okay, so what else do we have here? We have P or Q. Is that in CNF? Yep, that's already in CNF. Great. What about this guy here? Not, but apply to the conjunction. QR, because times multiplication is conjunction. So that is not in CNF because the only thing that can be negated are variables, individual variables. This time we're negating the result of a conjunction, which means, it is not in CNF yet. But how do we turn this into CNF? What is the only rule that I can really apply here? De Morgan's law. Okay, De Morgan's law is kind of like distributing a negation, but you also have to change the operator. So in this case, we are distributing the negation to the inside. So Q and R become not Q and not R. But then the conjunction in the original WFF becomes a disjunction. Okay, so the next question is that a CNF? It's a CNF because it is a disjunction of variables or the negation of variables. So now we have 3 CNFs. So what does that mean? That basically means that all the known facts in this particular system, everything in iota that really matters to us, can be summarized as this. Not P or R, and P or Q, and not Q or not R. That is one CNF. And that one CNF captures everything that is known to be true already. Is that part okay? Yes? No? Okay. What are we trying to prove? We are trying to prove this particular thing here, and I think it is a theorem, okay? I think given the known to be true facts, we can also establish this particular implication. I think we can come up with a conclusion of everybody passes cisp440 implies all soy milk spoils. Okay? But I don't know for that. I don't know that for sure. I need to prove it. So in order to prove theorems using resolution, we also need to use proof by contradiction. And proof by contradiction is done by this part here. Okay, that's something that we talked about last time. So in proof by contradiction, what we're going to do is we have to negate the theorem that we're trying to prove, put it into the known facts put it into the facts that are known to be true, and then see if we can get to a contradiction. So this is the theorem that we're trying to prove. Okay, so I'll just write it here. Theorem to be proven is R implies Q. But we don't throw that into the CNF. We throw the negation of this into the CNF. Okay, so now we have to say negation of the theorem to be proven. Okay, so when you look at the negation of a theorem, what you need to do is simple. You just put a big old negation sign on top of the entire thing. Okay, so you just say, okay, if the theorem itself is R implies Q, then the negation of the theorem is the negation of all of that stuff. Is that okay? The theorem itself is a WFF, and then the negation of the theorem is the negation of that WFF. Okay. But we also want to turn this into a CNF, so we will say, okay, what can we do about this? I'm not going to do anything about the negation because I need to take care of the implication first. So we say this is the same thing as not R or Q, because R implies Q, by definition, is not R or Q. And then now we can say, okay, we have a negation on the outside of a disjunction. This is not in CNF yet. Then the only thing I can apply here is De Morgan's law, because this is the other De Morgan's law, which means that we are distributing the negation into the inside, and this time we turn the disjunction into a conjunction. So now we throw everything in. So we distribute the negation to not R first, and I know double negation can be canceled out, but I don't want to do it just yet. And then not Q is the other component. There's a multiplication in between here. Then we do the really kind of the next simplification, which is Q, which is R, not Q, because double negation is not useful. We just take out the double negation. Are there any questions about how I turned the negation of the theorem into a CNF? Is that okay? All right. So the proof is now involving the original CNF, which is capturing all the known to be true facts. Okay, we don't question those, and also the negation of the theorem that we are trying to prove. So we put all of these things into one gigantic, well, this is not really gigantic, but it's big, okay? It's longer. So we put everything into one single CNF, and then we say, this is the big question, okay? The question is, does this lead to contradiction? That's a question, okay? I don't know yet. So when we get to this point, you can try to use Boolean algebra, okay, to prove that this either leads to contradiction or does not lead to contradiction. But that will kind of throw us back into the problem that we had earlier. Okay, because if you want to use Boolean algebra, then you have to think about, okay, but which rule should I use first? And is that going to help us, or is it going to send me to the wrong direction? So it doesn't even come close to the solution. We don't want that. Okay, we want things that are easy to do, mechanical, and will definitely terminate. That's what we like as programmers, as computer scientists. So instead of doing this, using the conventional proof, what we're going to do is we're going to use resolution. I think that's a fly and not a mosquito, because if it's a mosquito, then I have to stop the class and actually get it first. All right, so we want to use resolution. How does resolution work? Okay, so let's take a look at this one here. and say, how can we resolve this? What does it imply? Okay, let's take a quick look at resolution itself. Okay, so when we talk about resolution, we basically want to have two disjunctions, okay, one like this and one like this here. One involving a variable that is not negated, the other one involving the negation of that same variable. If you can identify two disjunctions like that inside the long CNF that we have, then we can say, oh, okay, we can actually come up with a new term like that one, so that we can add a new term to the CNF without changing the meaning of the CNF. Okay, so the result or the consequence of this particular inference is really the concatenation of these two, of what you're supplied with, but with the subtraction of the variable that basically has one that is negated and the other one is not negated. You can kind of look at this as concatenation, except the variable that connects these two expressions annihilates itself, because on one side you have a negation and on the other side you don't have a negation. Okay. And the reason why it works is explained here. So I'm not going to go through this because it's not the focus of today's class. So I'm not going to focus on the proof of why it works. I'm just going to say it works. So let's go ahead and apply it and see how it helps us to prove our theorem. Okay. So knowing that is the theorem, can we resolve these two? Can these two be used in a resolution? It can be, because on one side we have a negation of P, on the other side we have the non-negative version of P. So let's go ahead and resolve these two. Okay. So when we resolve these two, I'm just going to use an indication here, just so that we know which two we are using for the resolution. Okay. So I can copy the original form all the way over here, because all of that stuff is still true, except we can add one more term, which is the result of the resolution. What is the result of the resolution?
R or Q.
R or Q, very good. Okay, so we have R or Q. And the reason why we have R or Q is because when we combine these two using resolution, we take out the P and the not P, and then we keep everything else the same and concatenate the rest of the components. So that's how we end up with R or Q, because P is gone, not P is gone from the other one, so we're only left with R or Q. Okay, very good. When we look at this thing here, can we resolve using, is there anything else that we can use here to resolve? Okay, we already used up the first two, so we can look at the first and the third. Looks like the first and the third can resolve as well. So you can see it's a very mechanical process. I'm not even thinking much about, what is the quickest way to get to a contradiction? I'm just saying, okay, what is applicable? What can apply? Okay. So in this case, I am going to use the first, which is this one here, and the third, which is this one here, and say, okay, these two sounds like they can be resolved because one has R and the other one has a negation of R. So these two WFFs can resolve into a new term. So now we say, okay, let's copy the first chunk of this, and then we want to state what is the actual result of the resolution. What do you think is the result of the resolution?
Not Q or not P.
Yep. Okay, so we say not P or not Q. So I try to maintain the alphabetical order just so that it's easy. Well, I guess I didn't exactly follow that rule with the previous one. Okay, but not counting the alphabetical order. Yep, question?
How can we keep the two that you did the resolution on? I thought
You can keep them.
they equal the.
So that he could use them. So that he could use them later.
Yes, you can use the result. You can use them again.
Okay.
Yeah, because the whole point of not just resolution, but the whole point of using inference rules is you're just adding more things to the map. What you have already should still be there. Is that okay?
Yeah.
Proving it, okay, this is kind of on the side note here. When you're proving things, you're not really creating anything. You are actually trying to discover a path that is already there. It's just a matter of knowing how to walk that path. It's like navigation. Okay, proving is a navigation skill. It is not a discovery skill. You're not creating anything new. Everything, all the spots are here to begin with. But by applying, all these steps in proving, you're just discovering. Oh, okay, this is actually a WFF that is true. This is a WFF that is true, and so on. You're basically just navigating through the things that are already true to begin with. But when you're proving, you're just saying, okay, now I see that that is true too. Now I see that is true. So you're discovering a path from the known facts to the thing that you want to be proven, that needs to be proven true. Okay, so now we have this expression here. And then we say, okay, when we look at this, is there anything else we can resolve here? I have matched the first thing here to the second and to the third. I think we used up everything already. So we can look at the second one and say, can the second one and third one be used to resolve something? Well, looks like they can be combined because one has a Q, the other one has a not Q. So let's take care of these two. But you can also see that this is kind of a very systematic way. Well, wait. If I want to be systematic, let's match the first one to the fourth one. Because they seem, nope, they cannot be resolved, never mind. Okay, so we want to look at the second and third and say, hey, these two can resolve because of the variable Q. Because the first one, P or Q has Q non-negated, and the second one has not Q or not R, which is negated, so they can resolve. What is the result of the resolution? Yep, you just do the concatenation and throw away Q, right? So it becomes P or R. Oh, not R. There we go. Are we doing okay so far with how we perform resolution? Is that okay? It's pattern matching. Okay, you just basically say, what do you have? What do I have? Do you have the negative version of one of my variables? If so, we can resolve. Yep.
Which one did you do to get that?
These two?
Oh, okay.
Yeah, I put a kind of fake underline to indicate which two we are resolving. All right, so let's go ahead and start with this one. You can see the CNF is getting longer and longer, but are we gaining more information? Are we actually, is it different from the one before? If you are to use a truth table of all of these longer and longer CNFs, do you think that those columns would look any different from the original one?
No.
Nope. Exactly. So that's actually what we are trying to do here. We are just basically trying to come to the contradiction. All right. So we have just resolved the second with the third. Oh, I just erased that. Let me go back and add that back here because I want to document which two are we resolving. So now I want to try the second one with the fourth one. You can see this is really systematic. I'm just doing an exhaustive search of what can and cannot be resolved. So we can resolve these two, okay? Because one has, oh wait, I'm missing a plus here, aren't we?
No.
Oh, I'm missing something that's kind of important because this one is supposed to be two individual components. Okay. I haven't made a mistake yet. It's just that notation-wise, it's best to separate these two into two components to the conjunction, because otherwise it looks like it is a disjunction, but it's not. Okay. All right. So we can now get back to our original thing. So we look at the second one and say, can anything else resolve with it? Well, we cannot resolve it with the third one. We can resolve it with the fourth one, right? So if you look at this one here, it has Q, and then this is not Q all by itself. They can resolve. Because not Q, if you say, oh, not Q, you're so lonely, everybody needs a companion, okay? So how can we make this expression to have a companion? Just artificially. We cannot use and inside the parentheses or false, right? We can always do that without actually changing the meaning of the expression, right? So now we can say, oh, now we are good. We can resolve this with this one over here, Okay, so we'll go ahead and denote that and say that this expression can resolve with this one here. And what is the result of this resolution?
P plus 0.
Okay, so the result of that, okay, we are running out of space. So the result of this actually is just P. Because P or false is just P. Okay, I'm adding that or false just to emphasize that even if a variable is all by itself in the conjunction, it can still be used to resolve something else. Okay. Okay, so let's go ahead and take this expression and say, okay, can we resolve it any further? Yep, question? Go ahead.
When you get R and not Q, that's the CNF
R,
at the very top. When you negated the theorem.
R not Q?
Yeah.
That is a CNF because it is actually, that, right?
Okay. So
It is already a CNF.
It's just one. You can have a conjunction of two variables. CNF.
Okay. Okay. So to understand why this is a CNF, you have to say, okay, is R by itself a CNF?
Yes.
It is by definition a CNF, right? What about the negation of a single variable? Is that a CNF? It is a CNF by definition. So by definition also, if you have two CNFs and you do a conjunction of the two CNFs, the conjunction itself is a CNF. So that's how we know this one is a CNF already. All right, so we look at this big mess here and go like, okay, what can we do here? So I'm still kind of looking at the second one and see if it can resolve any further. So we want to look at this one. Oh, this is a good one. Okay, I want to look at this one and the one that we created a little bit earlier, which is this one here. So we want to resolve these two. Okay, but this is a really tricky one because it really helps to emphasize that we can only resolve one variable at a time. You cannot just say, oh, this one has got P, that one has got not P, this one's got Q, that one has got not Q. So we can annihilate both variables at the same time. Doesn't work that way. Okay, you have to choose one variable only when you perform resolution. So in this case, you have a choice. Okay, you can say, okay, I want to use P for the resolution. Fine, not a problem. Or you can say, I want to use Q for this resolution. That's not a problem either. But you cannot use both at the same time as a single step of resolution. So keep that in mind because a lot of people look at this and go like, hey, we can annihilate both of these variables at the same time. You cannot. Okay. So what I'll do is I'm going to pick P as the resolving variable and then keep the rest. Okay. And you can probably see the rest is really kind of silly. Okay. Once we are done with it. So instead of using this way, sideways, I'm running out of space horizontally. So I'm just going to use a vertical method to show the result of this. Okay. So after resolving these two, and I'm taking P out of the whole thing, so we end up with Q from this one, and then we end up with not Q from the other one. Right? But then I can do a simplification, can't I? Because what is Q or not Q? It is guaranteed to be true or 1, right? So I'm doing this really step by step because I want to show you guys, how to do it step by step. So this becomes just 1. Is that going to be helpful to me? And true doesn't do a single thing, okay? Which also means that we don't even need that because it serves as no purpose. So this particular step of resolution is useless. It didn't help us in any way. Okay. Okay, great. Anything else? Anything else we can resolve that gives us something new? Okay, so you take a look here and go like, let's take a look. We have the second one matching with this one, second one matching with, it won't match with any of the last ones. So now we start with the third one, which is this one here. And then we say, can it resolve with the fourth one? Yes, it can. Okay, so let's do that. So we are resolving the third with the fourth. Because one has not R, the other one has R. So when we resolve these two, then it becomes what? Okay, that's actually a dead end here. What do we get?
Not Q plus 0.
Yep, not Q or 0, and the or 0 doesn't need to be represented. So what do we end up with?
You already have it.
Say again?
You already have it.
We already have it. Very good. Because the R and the not R annihilates each other, and the not Q is already here. So we have, so it doesn't give us any new term. Okay? It's useless. Is that making any sense? When we resolve these two, this is the first time we try out these two, okay, resolving these two. But when they resolve, they only get not Q left. But not Q is already one of the terms here, it's really the next one. So that means this particular resolution doesn't get us anything new. Okay? All right, so it's not useful and gives us exactly the same result as last time. So next time, for the next resolution, I will consider this one with this one here. Cannot resolve because they both have not Q. And then we look at this one, and then the one after that. Okay, it does resolve, right? But it has the same pattern as the other one, which means it's going to resolve to what? Just one, which is not useful. So now we say, okay, that's not going to be productive. So we look at this one versus this one here. They cannot resolve because the only common variable is Q, and both have negated version of that. And then we look at this one and the last one, which is this one here. They cannot resolve because even though they both have R, but they're both negated, so they do not resolve. And then we look at this one as the last one, and they do not resolve either because they do not even share a single variable. So now we are done with the third expression in the CNF. But are you guys seeing how this is really mechanical? It's kind of having a double loop. The outer loop just goes from the first to the last, and then the second loop goes from whatever is next to the first one and keep going and try resolving. So do you think that kind of loop will terminate at some time? It has to, okay? Okay, so just to be complete, let's go ahead and look at the fourth one because we're done with the third one. So the third one is R. It cannot resolve with not Q. It cannot resolve with R or Q. It cannot resolve with not P or not Q. It can resolve with this one, but we already have P at the end. And it cannot resolve with this one because they don't share any variable. Yep?
Sorry, never mind.
That's okay, not a problem. Okay, let's look at the third one, the fifth one now. Okay, can it resolve with the next one? Yes, it can, but it only results in R, which is already here. So it doesn't give us anything new. Can it resolve with this one? And the answer is yes, it can. Nope, it cannot because they both have negation of Q, so it cannot resolve. So can it resolve with this one here? Cannot. Can it resolve with the last one? Cannot. So now we look at the next one. So we can basically see how this goes. This one can resolve with this one, which ends up with R or not P, which is the first one. Okay, so it's already there, so it doesn't give us anything new. Can it resolve with this one? It resolves to P or Q, which is already here, and it doesn't resolve with the last one. So it doesn't give us anything new. It does not. It's not productive. And then we look at this one here. But can you guys see how mechanical this is?
Right.
It's just moving on to the next one and say, okay, can you resolve with everything that is after you? Okay, yes, we resolve, but it doesn't give us anything new. No change to the overall CNF, and so on. So we're almost done here. This one and this one can resolve, but it will give us not Q or not R, which is already here. Not productive. It also resolves with the last one, which will give us not Q, and not Q is already here. Not productive. So we're only left with these two here. These two cannot resolve, so we are done. In other words, once we get to this point here, we are stuck. No matter which two sub-expressions you choose to resolve, it doesn't gain us anything new. is that contradiction itself? Is this expression, even though it's kind of long, is it always false?
No.
Nope. Which also means that the original theorem that I thought was true is
True.
I'm trying to use proof by contradiction.
Oh.
I could not get to contradiction, which means
It's not true.
the theorem is not a theorem. Okay, that WFF R implies R implies Q is not a theorem. But the nice thing is, one, there's only one real rule that you're applying, okay, other than commutative to change the order of variables. There's only one thing that we're doing. We're just matching a disjunction versus another disjunction and say, do you have one variable that is the negation of one of my own? If so, we can resolve and come up with a new expression, but then you just have to say, okay, but is that expression already in the CNF? If it is already in the CNF, don't do it. You know, don't bother to add it. If it is not, then you add it to the end of the CNF. Is that mechanical? I think that's really mechanical. Are we good with the process so far? Yes?
Okay, so we're trying to prove the original thing.
Right.
But then we're doing negation. And so can you just go over again what the result of this would look like if we did prove the original? Like you're saying that we didn't prove the original because this didn't go to
it doesn't get to
zero?
a contradiction. So if this thing here was actually a theorem or a consequence of the known facts in the system, then we would be able to get to a zero in the resolution steps.
Okay.
But since we were stuck in the place where it is not a contradiction, it's not a zero, that basically says this is not a theorem. It is not a result of the given facts.
Okay.
Yep.
So if you get a 0 anywhere, can you stop?
Yes. Once you resolve to A0, then you can just stop because anything and false is false. So once you get to one single false, you're done. The whole thing is false already. You have a contradiction. And you can congratulate yourself. We have a contradiction now. Because that's what we want. We want a contradiction. Are we still okay so far with the mechanism itself, the how of everything? What are we doing? Not even caring about the resolutions, which one resolved with which other one. What have we been doing for the past half hour or so? We're using resolution to do what?
To check and prove by contradiction.
To apply proof by contradiction. In other words, we were trying to prove a theorem. Okay? And why are we doing it this particular way? Why are we not using Boolean algebra to prove the theorem? Why are we using this kind of really awkward but really mechanical way to prove theorems?
Because we might be able to put that into a computer program.
Because this is easy to code, exactly. Okay, this is easy to code. cisp440 is a code requisite of this class, but I'm assuming all of you have taken cisp360 or a equivalent class already, right? So looking at the process of what I just did, do you think you can write a program to do all this? Not that I'm going to assign it as a homework assignment, but if you're given enough time, do you think you can write a program to do this? It's a triple loop kind of thing, right? You just keep looping, but it has to terminate. The reason why it really has to terminate, I think I explained that in the previous lecture, but it is important to kind of talk about it again. So even though when you apply resolution, you end up with a new term that you also append to the end of the CNF, the new term always has one fewer variable. So as you apply resolution, the terms that you're adding to the CNF always have one fewer variable. So the more you apply resolution, the newer terms get shorter and shorter and shorter. And at some point, they will become single variables. And you cannot resolve any further. So either you get to a contradiction, which means you're done because you have a contradiction, the theorem itself is true because the negation of the theorem leads to a contradiction, or you're stuck at a place where we are currently at. Okay? There are no more applicable resolutions. Then you also come to a conclusion. and say, okay, I'm done here because I cannot get to a contradiction. And as a result, the theorem is false. You have just proven that the theorem cannot be true, which is also good. So here are the three questions, right? The why, we like it mechanical because now we can actually code it in a program, and the program or the algorithm is guaranteed to terminate. And it's an easy program to write because there's no intelligence whatsoever in this program. It's just a triple loop kind of thing. 2, what are we doing? We are trying to prove theorems. And then 3, how are we doing it? We are using resolution as a mechanism. So are we okay with those 3 things? Are we connecting the why, the what, and the how of what we are just talking about? Yep.
So as soon as we can produce a false binding to TNFs, we're done.
Yes, absolutely. That's actually what we want because we're trying to prove a theorem to be true most of the time. But since in this case I cannot get to the contradiction, it is also good because we just say, okay, this theorem is not true. It is not a result of the given facts, which is also good because at least we terminate. At least we get to a point of a conclusion and say, nope, that's not a theorem. All right. So I'm pretty sure some of you are really disappointed because it's not a theorem. So we move on to example 2 where it is a theorem. So we want to basically do this all over again, but applied it to a different conclusion or potential theorem. So in this case, we keep everything being the same except the theorem that we want to prove is R implies P and not Q. Okay, the other one has Q instead of P. So we want to say, okay, can we prove this? Okay, so I'm going to reuse a lot of this stuff here because I can reuse everything up to this point. Okay, so I'm going to copy and paste it just so that we have a fresh copy. So I'll copy here and paste here. And I'll just kind of scroll everything up so that this way it's not interfering with what we're doing here. So this time the theorem that we want to prove is almost the same as the other one, with the only exception that we are trying to say R implies P instead of R implies Q. So we have to go through the same thing here. The negated theorem is the negation of R implies P, which is the same thing as the negation of not R or P. And then you apply De Morgan's law. So this becomes not R, not P. But then you can say, oh, we can simplify because double negation doesn't do a single thing. So we can say, oh, this is just R, not P. And then you can just separate those two so that it is clear that this is a CNF. Okay? Are we still doing okay so far with this second example? So now we say, okay, let's make one huge CNF, combining the known facts and the negation of the theorem. So now we basically have the gigantic CNF being this thing here, combined with this thing over here. And then we say, okay, how do we resolve this? And I think I can come up with a slightly better way to do this. Okay.
So are we not changing any of the nouns?
Nope, we're not changing any of the knowns. We're just saying, okay, let's try to prove another theorem.
With the nouns?
It's the same stuff. Okay, we're still claiming the very same things that are true to begin with, the same iota, so to speak, but we are trying to prove a different theorem.
What's the different theorem?
The theorem is this one. This is our new theorem to prove. The one that we dealt with before is R implies Q. This is R implies P. Yep.
So just to clarify that first step, we negate our original theorem and then add that to the CNF and then try to see if that equals 0.
Yes. See if we can resolve to a 0.
Okay.
Yep. Okay, so I'm going to do it the very same mechanical way. I'm pretty sure some of you can already see, oh, that's an easy one. But we'll do it the mechanical way, okay? Because we like it to be easily programmable. And anything that is really kind of mechanical is easier to code. So we look at these two and say, wow, we can resolve that, okay? So we can resolve this. So when we resolve, we just copy the original thing and just append the result of the resolution. So in this case, we are getting rid of P, not P. We're only left with QR. So we end up with just Q or R. Are we okay with this first step of resolution? And then we look at the resulting thing here, and then I'm doing it very mechanically, remember? So I'm now looking at the first one versus the third one, and go like, hey, this can resolve too. Let's go ahead and resolve those two. In other words, I am not even applying any type of intelligence or optimization thing that only people can do. This is something that your program can do with a double loop. Okay? So we resolve these two, and then we end up with, let's see here. Okay, when we resolve those two, we get rid of the R, the not R, so we end up with not P or not Q. Right, there we go. And it's new, okay, because if it's not new, then we don't append it to the end. Okay, so now we look at this whole thing here and go like, can the first one resolve with the fourth one? Nope, because they're not, this one is not negated. Cannot resolve with the fifth one, cannot resolve with the last one. So we are done with using the first sub-expression as one part of the resolution. We're now moving on to the second one. So we look at this one here and go like, can it resolve with the one right next to it? Yes, we can. Does it come up with anything that's new to us, which is P or not R? And that is new as well, so we will go ahead and resolve these two. So we now say, okay, starting with the second one, resolving with the third one, we end up with a new expression, which is P or not R, like that. Do we have any questions about the individual steps, how I choose which two to resolve and the result of the resolution? It's really mechanical, okay? All right, so looking at this thing here, I'm really being mechanical. So I look at the second one and look at the fourth one, cannot resolve. Look at the fifth one, it can resolve to a single variable of Q because the P annihilates each other. So we are only left with the Q, so we'll go ahead and do that one. So we say, look at this one here, they can resolve. And the result of the resolution is just, what did I say? Q all by itself, right? And then we look at this longer CNF, and then we start with the second one. Remember, I'm trying to be very, very mechanical. So looking at the second one, look at the next one here, they do not resolve. Look at this one here. It does resolve. Nice. Because in this case, well, they do resolve, but it's useless. It's a useless resolution because it has the same pattern as last time. One has all the non-negative variables. The other one has all the negative variables. I'll go ahead and do it anyway, but I just want to show you that the result of the resolution is not useful. So we'll go ahead and do this one more time. We have seen it already before, but it doesn't hurt to do it just one more time. Okay, so after resolving these two, then we end up with Q or not Q, Q or not Q. But Q or not Q is simplified to 1. Anything and 1 is just whatever we start up with, so it's useless. So that resolution, even though we can do it, it doesn't give us anything useful. P or Q does not resolve with any of the last two, so we are done with using the second one as one of the components for the resolution. So now we start with the third one. We look at this one here, and then we say, hey, it can resolve with this one and resulting in a not Q. Okay, so let me just highlight which two we are resolving. We are now starting with the third one, and it does resolve with the fourth one because one has a not R, the other one has a R, so they can resolve. So the end result of this particular resolution is adding not Q to the end of the CNF, right? So most of you should see that we have a contradiction already because we have Q and not Q at the very end of the CNF. So if you program your loops correctly, you can basically just spot contradictions like right away and say, okay, we're done. But let's just say that I write an algorithm that is really stupid. Okay, and it doesn't terminate because it's smart and spot that. Okay, but it doesn't. Okay, trust me, it's not really that bad. Okay, it's not that bad. Can this resolve with this one here? Nope. Can it resolve with this one? Yes, it can, but it just gives you something that's useless. We already know that pattern. Can it resolve with this one? And the end result is
No.
it won't resolve because there are no opposite polar variables. So can it resolve with this one? No. Can it resolve with this one? Yes, it can, which will give you a not R. Okay, so let's go ahead and do that resolution because I just want to do it very mechanically and just say, okay, these two. Okay, which one are we talking about? Q. So these two can resolve into, okay, so it resolved to not R. So at this point, there are two contradictions already. But because the algorithm is dumb, it has not spotted the contradiction yet. Okay, so we keep moving, and and we ask, can this resolve with the last one? You cannot. So we're done with this one. So now, finally, we start with this term here as the first term for the resolution. And we say, okay, what can this resolve with? Not this one, not this one, not this one. It does resolve with this one because R is one side and then not R is on the other side, and it resolves to a single P. Okay, so let's go ahead and do this resolution because remember I'm trying to be as dumb as I possibly can be because this makes the program easier to write. Right? Makes you wonder why certain operating systems are less efficient than others. Okay, you guys are not getting my joke?
Is that a Java Windows?
Well, I mean, I have no idea why because I'm not an employee. I cannot see the actual source code.
This is us just trying to guess at the ineptitude. How does this happen?
Well, I don't think it is it's a problem with the developers. It's a priority issue with the company itself. In other words, if you are employed by a company where releasing a new version because it generates revenue from licensing, so if you're a developer for that company, say, hey boss, I can make this program go twice as fast. Okay, just give me a month of time and I'll make the operating system go faster. Your boss, will come back and tell you, let's not waste time on that because computers are always getting faster and faster. So there's no value in making the operating system any more efficient. Instead, let's work on the next GUI thing and something that we can hype it up so that we can sell the next version of this program to end users. So your boss is going to prioritize for you and say, okay, let's not optimize, let's not fix those little things that are useless as far as revenue generating is concerned, and we'll focus on things that can actually be used for advertisement purposes, to convince end users to upgrade and stuff like that. So I don't think it's an issue with the individual developers. I think it's a prioritization issue with the company itself. But that's just my theory. And I cannot prove that by resolution. Okay, so getting back to this really dumb one, because now I have ended up with a P, which means we have 3 contradictions now, okay, which is the maximum that we can get because we only have 3 variables, right? But this algorithm is so dumb that it's not stopping yet, okay? So it's still staring at the R and say, what can resolve with a single R? Okay, the next one cannot resolve. We get a not R over here. They can resolve. Now, when these two resolve, you go like, well, but they annihilate to nothingness. Okay, so what is nothingness? What is, parentheses with nothing inside? Well, that's one way to look at it. The other way to look at this is to say, well, this guy has a hidden companion, right? And this one has a hidden companion as well. So now they can resolve, right? Because they both have a companion. So we can look at these two, and I'll indicate which two we are resolving. So we are resolving this guy with this guy over here. I don't know how many of you watched Babylon 5, but in Babylon 5 they have a species called the shadows. So the plus 0 is kind of like a shadow. It is there. You just cannot see it most of the time. Okay, you guys are not getting it.
It's a good show.
It's an extremely good show. So if you look up Babylon 5 shadow, and yeah, you want to watch one where it's just a optical aberration. Oh, these are shadow ships. Oh, come on. Okay, we'll look up the one with Kosh in it because Kosh got killed by a bunch of shadows.
How quick to give away nature?
Okay, well, I guess I really should not be spending too much time on this. But anyway, these are transparent or creatures that can hide themselves. So anyway, getting back to what we are doing here, because we're done. We're pretty much done here. Because when we resolve these two, then we end up with 0 plus 0, because the two hidden companions now show up next to each other. But 0 or 0 is false, or false is false, and anything. Okay, we'll make it very, very step by step here. Okay, this simplifies to a single 0, right? But if we have a huge conjunction, and one of the things that you are ending with is a false, the entire thing is a false. Congratulations, you have a contradiction, which is a good thing in this class. Because when the negation of a theorem results in a contradiction, it means the theorem itself is true. So we have just proven that R implies P is true. Are we doing okay so far with this particular example? So in the second example, we did end up proving the theorem is true, as opposed to the first one, which we ended up proving that it is not true. Are we doing okay? All right.
So in that first example, you basically have to run through all of them to know
Until until you get to a dead end.
Yeah.
Yep. A dead end meaning that you can still resolve, but it doesn't give you any new terms.
Yeah.
It's basically just giving you terms they already had in the system.
Whereas here you can early exit as soon as you.
Right. If I
0.
were smarter,
Yeah.
if the algorithm was a little smarter and spot the contradictions, I could have stopped a lot earlier. Because the first time I can stop is when I spotted, I think this is the first time we can stop.
So you can store the single variables as soon as a negation appears.
Right.
You're done.
Yeah. But that requires some special code in the condition of your loop.
Yeah.
So instead of doing that, I just say, okay, keep resolving until we actually get a 0. And in terms of coding, the second method is less optimal, but in terms of simplicity of the code, it is actually simpler because you're not making special cases.
And you can resolve, I don't know, can we go beyond 3 variables, right?
Can we be on?
Beyond the 3 variables.
Oh yeah.
So that's what I mean, so you don't have to always catch special cases or.
Exactly.
Actually, no, you can't, because if you state all the variables, you can always store it.
You're basically just spotting a variable
Yeah.
on one subcomponent of the CNF, and you're trying to spot the opposite or the negation of that variable as by itself as another component of the CNF. But it's a special case. We can do a lot of things because we can apply what I call the eyeball algorithm. But your computer, it's really hard to program eyeball algorithms into a computer. So that's why I try to stick with really mechanical methods, so that it is easier to code and it still gets you the result anyway. All right. So any questions about this? No questions? Okay. So if there are no questions about this, we are going to take a look at your homework assignment, which is called CNF assignment. I really should probably give you the second one as well, proof by resolution, because we are done with this entire topic. So with this one, there are 4 variables instead of 3, okay? And this part here is completely optional. If you don't want to read this part, it's okay. Okay, it really is just it just makes it more fun. Okay, So when you look at this part and you combine it with the known to be true facts, okay, WFFs in the iota, then you basically say, okay, what does that really mean? Okay, we know as a fact that TAC is teaching cisp440. It's a known fact. No, take it back. That's not a known fact, but this entire thing is a known fact. Okay, TAC is teaching cisp440, or a gamer is taking cisp440 implies P, which is cisp440 is a boring class. That is known to be a fact. Okay. The second one is just another rule that is known to be a fact. P implies S. P is cisp440 is a boring class. That implies S, which is someone sleeps in cisp440. But does that say anything about cisp440 is in fact a boring class? Nope. It's just stating a rule that says if cisp440 is a boring class, then someone is going to sleep in the class. That's all it's saying, okay? And then the last one says it confirms that somebody is sleeping in cisp440. Okay? So I'm not even trying to prove any theorems here. Okay? This assignment does not involve proving. All it does is to involve resolution. So your job is to convert the WFFs into CNF, not even resolve. Okay? It's just convert everything into a CNF and turn this whole thing into a gigantic CNF. That's it. That's this particular homework assignment. And that's why I think I really should release the second one too, so that you can actually apply resolution to prove whether something is a theorem or not. So I'm going to do that after the class. I'll send you guys an email regarding that. And for this homework assignment, you can just use the notation that I used a little bit earlier. For conjunction, you can use quote-unquote multiplication. For disjunction, you can use a plus or addition. And then for negation, you can just use the exclamation point. Because I really don't see any reason why you have to go through the LaTeX stuff to use the wedge, the V, and also the negation symbol. Because when we get to for all, there exists, that sort of thing, I can see a big reason why we should do that. But in this case, there's no particular reason to do it. So I don't want you guys to waste time to format your answer when it's not really that useful. Are we okay with the homework assignment?
Do we type it in right in there, or do we?
Yeah, it will give you, the homework assignment will give you an HTML editor, and then you just type your answer in the HTML editor, which is kind of nice because you don't need your editor, you don't need to install anything, and when you submit your answer, it's automatically stored in Moodle, and you can always go back and change it before the due date. Okay. All right. So, any questions about all of this stuff here? No questions? Okay. So if there are no questions, I'm going to leave this topic as it is, and as I said a little bit earlier, I'm going to release the other homework as well, proof by resolution, which is actually what I did today. So that's going to be that, and we are going to have an exam 1 week from next Monday. Okay. So next Monday, we are going to have a practice exam in class. I will just basically give you guys the answers to the practice exam, explain all that stuff, and then 1 week after the practice is the actual exam. Yep.
So are the resolution and the previous assignment due on the same day, or are they?
Yeah, they're going to be due on the same day.
Okay.
Yep. But they should not really take you that much time. Once you understand the mechanism, it shouldn't take that much time. Right? Yep.
Could you prove that using a truth table?
Yes, you can. Now, that's a very good question. Okay, so the question is, can we prove the theorems, the one that we worked on earlier, using a truth table? The answer is yes. I'm not really sure whether I want to do it here, but let's go ahead and take a look. Okay. So this is the CNF representing all the known facts in the system. Remember that? Yep. Okay. And this is the CNF representing the negation of the theorem. Now, when you use a truth table to prove a theorem, you don't need to use proof by contradiction. Okay, so let me show you guys what I mean by that, and I'm going to actually do it using a truth table here. I'm just thinking what is the best way to illustrate. I'm going to use a spreadsheet to do it because it's a table, and it automatically widens and stuff like that. So that would be the best tool to do this. But that's a good question. It's a really good question. So we'll go ahead and copy all this stuff here. So we have 3 independent variables. We have P, Q, and R as independent variables. We also have the sub-expressions. So in this case, I'm just going to use the usual way for each column, P plus Q, and then we have not Q plus not R. And then we have the conjunction of those 3, okay, C and F of those 3. And then we have the theorem that we are trying to prove, which in this case is the non-negative version, because when you prove by a truth table, you don't want to use the negative version. The non-negative version is what you need. So we have R implies Q. Oops. R implies Q. It's the word. The spreadsheet is self-correcting. We'll just kind of leave the R as it is here. Okay. So the first thing we need to do with the truth table is to fill up the independent variables so that we have the 8 rows that we need to deal with. So in this case, we have 0. Okay. And then we have 1, 1, 1, 1 over here. One too many. And then we have. There are probably easier ways to do this. I'm just too lazy to do it the other way. Oops. Okay. So now we have the first expression. I can just use an equation here because in any type of spreadsheet, they know how to deal with logical operators. But then the other ones are zeros. I'll just do it by hand. Not P or R. I'm still thinking whether should I do it by hand or not. Because you can do it like using an expression or a formula inside a spreadsheet, but it wants true, false, and not zeros and ones. That's a problem. I have zeros and ones here. Let me see if it would do this or not. I think it would complain because the type does not match.
It's able to do it that way when
it does.
On another assignment. So.
Yep. So it does do it that way. So that's nice. It does recognize zeros and ones as true, false. I like that.
You just gave it an equation.
Sorry?
You just gave it an equation.
Yes, I just did the equation. I used the prefix format just in case to remind you guys. This is the prefix format, which means I state what I want to do, then I say, okay, what am I doing it to? Okay, it's the prefix format. So this is really nice because I can fill up this truth table in no time in this case. Because I can now say or, this is an or between the P, oops, okay. When you enter equation or formula in the spreadsheet, you have to start with the equal sign. And then I can just click on the cell that is supplying that particular argument. Okay. And then once you have one that is done and there's a pattern to it, you can just drag it using the lower right-hand corner. And we're done with this column as well. So now this is the last one, which is the or of the negation of Q, which is this one. And also the negation of R, which is this one. There we go. And we have filled up that column as well. All right. So the C and F is basically the conjunction of these 3. So you say and this one, comma, this one, and this one. And then you just drag this one over here. So this is the C and F of all the known facts. So are we doing okay so far with this particular truth table? Yep.
How'd you get the C and F?
The C and F is a conjunction of column D, E, and F. Those are the individual facts that are known to be true.
So it's an and. So it's an and.
It's an and, yeah. Because it's a C and F of those 3. Okay, so this is the theorem that we are trying to prove, which is R implies Q. I don't think implies is a function, so it doesn't have that. So I have to convert it into a negation of the first or the second. So this becomes an or with a negation to the R.
Couldn't you use if? If?
No, because that is not actually the same thing.
Okay.
So it's a not of this one, and then the Q is the second component, non-negated. So now I look at this one here. All right, so the question is, why is H, column H or R implies Q not a theorem of the known facts in this particular system.
Doesn't match with the CNF.
But it doesn't have to match, okay? Because we only need the CNF to imply, we only need the column G to imply the column H. Okay, as long as the implication works, they do not have to match exactly. So which row is indicating that G, the values in column G, does not imply the values of column H? Yes?
Oh, I mean, sorry, it would be call number 7, because that's true and false, so.
Yep, you're absolutely right. Because false implies true is true, not a problem. False implies false is true, not a problem. True implies true is true, not a problem. Yep.
Could you just do another?
Yes, I can.
A column that says
Yes.
implies
Yes.
theorem?
But I want to do it by hand first. False implies true is true, not a problem. False implies true is true, not a problem. True implies false is a problem. This is the one row that makes R implies Q not a theorem of the CNF. Because even though the CNF itself is true, what we claim to be a theorem turns out to be false for this particular combination of P, Q, and R. In other words, when P is true, Q is false, and R is true again, then what we think is a theorem is not true even though the original CNF is true. Okay? So we can also use another column to basically indicate just this fact here. Does the CNF imply our theorem? Okay? And the equation for this one is really just whether G implies H or not. So we basically say this is an OR, negation of column G, and a non-negative version of column H. And we want everything to be true in this column because we want for all cases the CNF implies the theorem. And as you can see here, we have one problem here because on row 7 we have a nope, I take it back. On row 7, we have a true implying a false, which is false. And as a result, the theorem is not a theorem. What we thought was a theorem is not. Okay, what about the second one? The second one has R implies P, right? So let's go ahead and change this to that one, okay? So we'll change the theorem to R implies P, and as a result, we have to change this one because it is P is column A and not B. Then we can just change this one here and drag it down, and that updates everything. Now pay attention right now, just look at the screen. Now we have everything being true on this side. But you can see that on certain rows, like this one here, on row 2, column G and column H do not have exactly the same value. That is not required. Because in order for something to be a theorem, we only need to say that if the premise is true, then the theorem has to be true. But what happens when the premise is not true? Well, we don't care. Okay. So we doing okay so far with this? So I have just demonstrated 2 ways to do theorem proving when it comes to Boolean algebra or propositional logic. One is to use a truth table, and the other one is to use resolution. Truth table is useful as long as you don't have too many variables, because the number of rows in a truth table is exponential to the number of independent variables. When you have 4 independent variables, you end up with 16 rows. When you have 5, you have 32, and so on. So it gets kind of busy after a while. Resolution, on the other hand, is more of a symbolic manipulation thing. So it is actually, well, in a way easier to deal with. Yep.
You keep talking about how resolution is like way easier to code because it's just mechanical. So how is there like a special library that you can use for all these like set notation functions like the and or the or the negation stuff?
What you can do is just use strings and arrays of strings for that purpose.
Okay.
So you basically look at each variable to be an object that has 2 parts, okay? Whether it is negated and what is the name of the variable. So you use that to represent a variable.
Mm-hmm.
And then a component in a CNF becomes an array of those particular objects, right? And then the CNF itself becomes an array of the other type. And then once you have that, then you can match things relatively easily, because you can now match, whether this sub-expression and this sub-expression do they share a variable where one is negated and the other one is not. It's just a cross-match thing. Okay. Any other questions? We are running out of time today, but you do have your homework assignment, which is really a combination of everything that we have talked about up to this point. All right. Okay, I'll see you guys next week. I do have my office hours if you need help or explanation of any of these concepts.
I didn't know spreadsheets were actually useful.